Good evening, everyone, and welcome to this very special event. It's a real pleasure to see so many of you here for this special lecture by Professor Haldane. I let the scientific introduction will follow, but let me just welcome firstly a lot of the undergraduate students who have come from a number of colleges and institutions from across Bangalore. I'm glad you came all the way across town for this lecture, and I'm sure you won't be disappointed. Let me, for those of you who are here for the first time, just let me say a few words about ICTS. So ICTS is a new institution. We moved into this campus 3 years ago. Some of you may have come for our public lectures, but outreach is a very strong part of the mandate of ICTS, and we have a number of we've had a number of public lectures, the ICTS Distinguished Lecture Series has had a number of eminent scientists speaking in it. We have the monthly series of Copy with Curiosity, which is held at the planetarium. If you don't know about it, please visit our webpage. There will be a upcoming Copy with Curiosity on the 20th, the next, not this Sunday, but the Sunday after next, by Francois Boucher, and it'll be on cosmology, on how we understand the very early universe. The range of topics at ICTS, as you can see, cover everything in physics, from what you will be hearing today, from the properties of matter, atoms, and even smaller, very tiny length scales, to the cosmic length scales of the cosmology program, which is also going on at the moment, and perhaps many of you are participants in the cosmology program. So in theoretical physics, we have a very wide canvas of research as well as programs going on. We also have a lot of activities in mathematics and mathematical sciences broadly. Maybe some of our very popular public lectures have been in mathematics, and we recently had one at Christ University, which is part of our Einstein lecture series, another of our outreach activities. And maybe some of you were there at that. It had, I think, 1,500 people and was on the topic whether the universe is algebraic or geometric. So anyhow, this is just to convey to you a bit about the kind of things that ICTS does. And if you would like to follow our activities, please go to our webpage and subscribe to our newsletter, or on various social media outlets. You have the ICTS updates on our activities, so you can subscribe to them. On YouTube, we have all the past lectures archived, so if you're interested in watching some of the wonderful lectures that have already happened here, it's never too late. You can watch them on our YouTube channel, which is called ICTS Talks, just ICTS and Talks together. Without any further ado, I'll invite my colleague Shubhra Bhattacharjee, who's a condensed matter physicist at ICTS, to give an introduction to Professor Haldane and his work. Thank you very much.
Good afternoon, everyone. It's my great privilege to introduce today's speaker, Professor Duncan Haldane. So Professor Duncan Haldane is a Sherman Fairchild University Professor of Physics at Princeton University. Professor Haldane is a theoretical physicist with research interests in a wide variety of problems in condensed matter physics, particularly in behavior of strongly interacting many-body quantum systems, such as metals, superconductors, and magnets. Professor Haldane has made pioneering contributions in revealing essential role of quantum mechanics in these many-body systems. His research has particularly helped us to understand the role of the interplay of topology and quantum entanglement in such many-body systems. To name a few of his contributions that I'm more familiar with, he has made central contributions to our understanding of interacting spin chains and metals in one dimension, the topological defects and their periphases in quantum magnets, fractional quantum Hall effect, and Chern insulators, and characterizing many-body quantum entanglement through entanglement spectrum. His research is so central to our present understanding of modern condensed matter physics that it is impossible to do research in the field without encountering and using in an essential way some of his ideas. This has been acknowledged by the community in various forms, including awards and recognitions that he has received. He is a fellow of the American Physical Society, the American Academy of Science and Arts, the Royal Society, and he has been the recipient of many awards, including the Oliver Berkeley Prize of the American Physical Society in 1993, the Dirac Medal in 2012, and the Nobel Prize in Physics in 2016, along with David Kostelis and David Thouless and Michael Kostelis, for theoretical discoveries of topological phase transitions and topological phases of matter. So with that, let us welcome Professor Haldane to deliver today's ICTS distinguished lectures on topological quantum matter and entanglement, a second quantum revolution. Before we start, I'd like to invite Professor Spenta Wadia, the founding director of ICTS, to hand over a memento to Professor Haldane on behalf of ICTS.
Thank you. Well, it's a great pleasure to be back in Bangalore. Actually, the last time I was here, it was Bangalore, and this institute wasn't built, but things have certainly changed a lot in Bangalore. So anyway, thank you for the invitation, and I'm going to tell you a little bit about entanglement, a kind of weird property of quantum mechanics, and some of why people think it might help us get a quantum computer, and all kinds of other cool things that are happening in quantum mechanics today. Okay, so sorry. So these are the heroes of modern quantum mechanics. The laws of quantum mechanics really took their modern form way back about 90 years ago, almost 100, 1925 to 32 period, which really was what we call the first revolution of quantum mechanics. And this is Heisenberg, Schrödinger, the one with the uncertainty principle, Schrödinger with the wave function, Pauli with the exclusion principle, and Dirac, who discovered the positrons and negative energy states of the Dirac equation, and relativity in quantum mechanics. And so these heroes really sorted out the basic laws of quantum mechanics, and they've remained unchanged to this day. All tests of quantum mechanics have really confirmed that quantum mechanics is correct as far as we know. And so, you know, what has been happening recently? The thing is that just because you know that the laws of quantum mechanics, it's one thing to write down a few simple equations, but it's much more difficult to actually understand all the kind of cool things that they allow to happen. And if we go back to the example of electromagnetism, Professor Maxwell here introduced the last of these equations. He added this term dd by dt to in fact, the third equation here. It's actually the last equation. And once he added this extra term to the equation for really to satisfy a kind of logical inconsistency of the equations, he discovered that it predicted the speed of light, which was that predicted that light was an electromagnetic wave. So at the time, of course, people have always been kind of skeptical about these kind of theoretical discoveries, and they say, you know, that's what's asked at all these things, what's it good for? And in fact, that was a question that apparently Gladstone, who was later the British Prime Minister, but actually I think he was a finance minister at the time he asked this. He said, that's very interesting, Mr. Professor Maxwell, but you know, what's it good for? And Maxwell is supposed to have replied, he couldn't say, but he did know that one day it would be taxed by the government. And of course, it's taken many years for all the technological possibilities of electromagnetism to emerge after 1864. And really the much of the 20th century involved, basically finding what you could do with electromagnetism and radio, television, etc. And in fact, it's still a field in which new discoveries are being made. Of course, things like the laser, which couples electromagnetism to quantum mechanics, has played an absolutely crucial role in our technological development. But even purely electromagnetic phenomena like what are now called photonic crystals is actually an active research area. So it's taken these equations have hide all kinds of possibilities which have taken a long time to really come to be discovered. Oops. So, starting around 1980, we started getting some new insights into quantum mechanics, and these accompanied unexpected discoveries. Physics and perhaps other sciences, but particularly physics, go through periods where some people think, okay, we've found everything there is to find, and it's usually some person who thinks that his work is the last word on the subject and there's nothing else to be done. But people were pretty kind of complacent. They were confident they'd found out most of the properties of condensed matter, which is a fancy term that means either solids or liquids. It's where the atoms are basically brought together in close proximity to form the regular matter that we're all made of. At the same time, Richard Feynman started thinking about what would happen if you started to do various things like engineering and computing on scale, using devices which had the scales as small as atoms. And he really launched this idea of quantum information theory and started thinking about what a quantum computer might do. And he made a very famous public lecture called "There's Plenty of Room at the Bottom," which is a play on words about a play at the time, a controversial social realism kind of play, which was called "Room at the Top." But anyway, so his talk "Room at the Bottom" discussed really what the difficulties and the possibilities would be if you tried to make machines and computing devices on an atomic scale where you couldn't avoid dealing with quantum mechanics. On the everyday scale, we can sort of get by without thinking about quantum mechanics, and of course that's why it took a long time to discover quantum mechanics, because you only really see its effect at the atomic scale, where you really cannot explain atomic physics without it. But for example, quantum mechanics is certainly everywhere around us. The reason you can ask, why do I not fall through the floor when I know that the atoms are the atoms which the floor and I myself are made of are all 99% empty space? And of course, Newton explained the reason why I don't fall through the floor by saying there was a reaction force acting on the floor, acting on my foot to balance the gravity moving downwards, and that's why I didn't fall through the floor. But that's just Newton's explanation is just an observation of what's going around it. It turns out, of course, that the Pauli principle, one of the four heroes I showed, is what stops me falling through the floor, because Pauli's principle says you can't put two electrons in the same place, basically, and the electrons which are in the soles of my shoe they detest being in the same place as the electrons in the floor. Okay, there are two kinds of particles. There's an unfriendly one called the fermions, which don't like to be together, and there's an Indian one called bosons, which bosons are they're very sociable and they like to get together, and they do like to be in the same place. And of course that was discovered by the Indian physicist Bose. So anyway, what's happened here? Okay. The experimental situation is that we're now trying to take control of quantum mechanics and use it in a way that we didn't before. Before, you do some measurement on something. It's like hitting something with a hammer. You find out what's inside it, but the thing is gone. The quantum information about it is gone. What we're trying to do these days is get a detailed control of quantum states, not by hitting them with a hammer and measuring them, but gently poking them and doing things to them which preserve them and allow us to get some control. And some people now think these new ideas which are coming from the marriage of quantum information theory with these new quantum states of matter have led to people having these dreams of a new future quantum information processing technology. And there's a lot of effort these days, and people are really starting to consider that we're now in the second wave of the quantum revolution, the second quantum revolution, where we're starting how to learn and control quantum mechanics rather than just observe what it does. And I suspect that in the next 10 to 20 years, there's going to be a lot of new stuff coming out. Okay. So anyway, that's the key message. So the key message, to summarize what I'm going to tell you, is that as we understand quantum mechanics better, and we're going to have new and possibly strange possibilities for the new materials of the future. People talk a lot about quantum materials and the new kind of technologies or quantum technologies that they can allow. These are vaguely at the beginning of emerging, and it's really a series of unexpected surprise discoveries that have led to this new way of thinking about quantum mechanics. Oops. So what's quantum information? There's a classical information in the computer of today is basically stored in a series of bits, which are really little binary digits, 1 or 0, which are really coded as a switch, which is either off for 0 or on for 1. And a switch can be viewed of a typical switch might be a little magnetic area where you have a little ferromagnetic area with the little atomic scale magnets, the spins of the atoms, all pointing all pointing one way or the other way, and you can take all pointing up to be to represent 1 and all pointing down to represent 0, and I can pass a magnet or something over the thing and feel whether the spins in whether the switch is on or off, or use it to control a current. So this is a classical system. There's a large number. All these guys are the same way, all up or all down, and there's nothing really quantum mechanical about these two objects. But the quantum information is actually stored in a single spin, a single one of these things. And now, instead of using the word spin, I might use the term qubit, which is the modern, the analog of the classical bit. It's the qubit, the quantum bit. And you read this, and this is any system which has two possible quantum states. It doesn't have to be up or down for spins. It can be anything. But anything which has two possible quantum states can be represented as a spin as a little arrow that's pointing somewhere in some three-dimensional direction on the surface of a sphere. So this thing is called the Bloch sphere, and the quantum information stored in a bit is characterized by this thing, so you can see there are really two basic angles needed to describe the direction of the spin, how much it's deviated from pointing upwards, and how much it's the bit that's in the equatorial plane is how much it's rotated. And so there's it's a lot more sensitive amount of information than just a single on-off thing. But actually you can't simultaneously record all of the information of the thing. You have to choose some direction to measure it in, and once you choose that direction, you can determine whether force it to be pointing up or down in that direction. So it's a little bit more subtle than the classical thing, but there's a lot more possibilities for storing and manipulating information in this device. So the central theme in this new approach to quantum physics seems to be this property, a weird property of quantum mechanics called entanglement. So when I started out in doing physics, I'd scarcely heard of entanglement. Entanglement was initially brought up as a kind of philosophical objection to quantum mechanics by Einstein, who pointed out that quantum mechanics predicted the existence of this very strange property called entanglement, and he felt it was like too crazy to be true, so he felt that once people tried to measure entanglement, they'd show it didn't exist, and quantum mechanics was a kind of fraud, or rather an approximation to a deeper theory which he wanted to find. but it was really something that was debated by philosophers of science rather than actual people involved in doing real science. It's right. So this was something that philosophers of science and people who got sidetracked from doing real science were worried about. And but in fact, it's changed completely over my career. Now, in recent years, it's changed from some kind of philosophical issue to a technological issue, and it's now recognized really as probably the central property of quantum mechanics, and it's now viewed as a resource or a fuel which will drive possible future technologies of quantum information processing. So, what was Einstein's role in this? Einstein was actually got his Nobel Prize not for his amazing discovery of first the theory of relativity and then the general relativity, his theory of gravity. He actually got his Nobel Prize. The citation was for his early contributions to quantum mechanics. In fact, it was really the second contribution to quantum mechanics after Planck. Okay. So he discovered the photoelectric effect, which is that if you shine light above a certain frequency on a metal, electrons get emitted and can drive a current, while if the light is below that frequency, if the light is blue, it will cause electrons to come off the metal, and if it's red, it won't. So this is very commonly found in a garage, in the device that stops a garage door operated by a motor from chopping your head off, because when you walk in front of an invisible beam, it cuts off the light, which stops a current flowing, and etc. So it was a very Einstein was recognized for his contributions to quantum mechanics, but by the time of around 1935, he'd soured on quantum mechanics, and as I say, he identified this entanglement property, which he denigrated as spooky action at a distance to kind of imply it was something that couldn't possibly be true. And on the other hand, the name that stuck, at least in the English language, is entanglement, which is a translation of the German word Verschrankung that Schrödinger gave it, a much more neutral word. Okay, so what is this entanglement? So as I said, one of these fundamental properties of quantum mechanics is this Pauli exclusion principle, the one that stops me falling through the floor, which again says that the two electrons can't be in the same state, which is roughly speaking the same place. But the thing is, in addition to being a charged particle that responds to electric fields, the electron also it behaves like a little spinning top, like a child's toy, spinning around its axis, and in addition to the charge and where it is, it's got this property called spin, which you use your right hand. It's really spinning in a given sense, but you can convert that to a direction of the little arrow by curling your fingers up and using your right hand in the so-called right hand rule for converting rotations to directions. So the thing is that the chemical bond that holds all of us together is actually made of two electrons, basically in the same place. So the two electrons can, the negative charge of the electrons will balance the positive repulsive charges of the two atoms on either side of the bond from the two ions on either side of the bond from moving apart. And so we're actually made out of these chemical bonds that glue all the molecules in our bodies together, and those are actually the central example of entanglement, because the way the electron avoids the Pauli exclusion principle is because of this extra spin degree of freedom. And what it means, the electron, if the spins are pointing not completely anti-parallel, then there's the second electron will be partly in the same state as the first electron. So the only way they can be in the center of this chemical bond is their spins are pointing exactly in opposite directions. And the Pauli's principle says that the electron is described by a quantum mechanical thing called a wave function, but the wave function has to change sign from plus to minus if I swap the two electrons around. So the actual state of the electron is not that the first electron is up and the second electron is down. It's actually a 50-50 mixture of the first electron up, the second one down, and the first electron down and the second one up. And there's a minus sign that if you swap the two around, the sign of this object changes sign. So this is actually the poster child for entanglement. This is the maximally entangled state of two electrons. And as I say, we wouldn't be here unless these electrons could do this and form this highly entangled state to hold all our molecules together. Okay. So where does Einstein come in? Einstein worried about the following issue. He wasn't so much worried about the entanglement of the electrons on this atomic scale, where they were very close together, like a tenth of a nanometer apart in a chemical bond. He was worried about what would happen if they were stretched. If you stretched this bond and made it very big, make it a meter big, made it 100 kilometers big, put one electron here and the other one on the moon or even in the next galaxy. Because the basic problem is that the entangled state was entangled only until it's measured. So the entangled state, until I actually try to measure it and look at it and see what it's actually doing, is a kind of fog here. I know there's one electron here and one electron here, and what I know is that if one is up, the other is down. But until I actually open the box and look at it and do a measurement, and determine, if I measure this one and determine it's up, I'll know that anyone who measures the other one will always find it down. And similarly, if I find it down, the measurer on the other side will always find it up. And Einstein thought that this implied that the act of measurement here caused some information or something to travel faster than the speed of light, because he said, how can you do something here and affect it so that the effect of measuring it here is instantaneously felt a long way away? And he felt that was a manifest violation of his principle of relativity, that no information can travel faster than the speed of light. Well, actually, it's not really a violation of this principle, because you can't actually send any information from the experimenter who does the measurement. The experimenter who does the, I'm going backwards. Yeah, the experimenter who does the measurement over here can't transmit any information to the person over here by doing the measurement. All they can do is they can agree to meet for coffee later on at a intermediate place and then discuss what results they got in their measurement. And of course, they'll always find that if he found up, the other one found down. Right? And in fact, you can of course if I had this laser pointer was sufficiently powerful and focused, I could point it at the moon and I could cause a bright spot to travel faster than the speed of light across the surface of the moon. But that's not a violation of relativity, because there's nothing actually traveling from A to B. It's an illusion, and somebody on the moon could certainly not use this moving spot to transmit information to somebody else far away on the moon faster than the speed of light. So actually there's no violation of relativity involved in the thing. But anyway, Einstein felt that it couldn't be that way, that when the electrons, the bond was stretched, there had to be the choice of whether the electron was up or down had to have been made right at the initial point when the bond started to stretch, and it couldn't possibly be this way. He wanted a theory called a principle of local realism to apply, that this couldn't be right, and he came up with this paradox as a kind of thought experiment that he felt that once people tried to carry out this experiment in reality, they would discover that quantum mechanics was incorrect. And hopefully he hoped it would lead to a more correct theory. In fact, one of his collaborators, this is all done in Princeton actually at the Institute for Advanced Studies, and one of his collaborators, Podolsky, actually went to the New York Times with this thing, and this was a day in 1935 that probably was a quiet day, that no country was invaded that day or something like that. So it made the front pages of the New York Times, Einstein attacking quantum theory, etc. And in fact, Einstein was very angry with Podolsky. I heard someone told me that he never spoke to Podolsky again because he felt, that scientists shouldn't be washing their dirty linen in public. He didn't like the idea of going to the newspapers about his attack on quantum mechanics. But anyway, so we had this this attack by Einstein, but it remained a thought experiment that no one did for a long time. Other people got into the action and tried to analyze this. I mean, David Bohm, who's famous for trying to have, among other real contributions, he's also famous for trying to come up with hidden variable theories like Einstein wanted to replace quantum mechanics, which never worked. But John Bell formulated Einstein's thought experiment in a much more clearer way, which involved not just measuring whether up or down, but making choices to measure which direction the spin was up. So the entangled electrons, they can be up, down, and down, up, but they're equally possibly be right, left, and left, right. There's an arbitrary choice you can make about which direction to measure. Ask is the spin pointing along or parallel to or anti-parallel to that direction. And Bell's tests involved experimenters making choices after the electrons, only making the choice about which axis to measure well after the electrons are separated, and things like this. And these are where all these issues about whether quantum mechanics is compatible with free will come from, because as we say, the actual experiments were done in 1982. Alan Aspey claims to be the first to have done it, although other people say there may be some other people who've tried similar things. But anyway, Aspey's measurements tested out the conditions of Bell. Bell basically came up with a set of inequalities that said if you do this measurement and you see such and such, it can't possibly be compatible with Einstein's idea of local realism, and the quantum mechanics would definitely say that the choice of what the particles were pointing in the direction was made long after was made when they were measured, not made when they split. And in fact, the only get-out clause of these in these experiments is this whole business of free will that says, perhaps perhaps we're all fooling ourselves that we think we have free will to make a choice. That maybe every choice we make in our life was preordained before we did it, and we're just living under the illusion that we have free will. But that's getting back into this philosophical issue. But from a practical aspect, Alan Aspey's experiments showed that the EPR entanglement entanglement can be made over distances larger than the chemical bond. However, it's actually very fragile. The chemical bond is very stable because there's a kind of large amount of binding energy, chemical energy that's holding it together. There's a kind of something called an energy gap that has to be overcome to break the bond. But as you stretch it, that energy gap becomes weaker and weaker, and it becomes a very fragile system. So while entanglement is viewed as the resource, spatially separated entanglement is viewed as the resource we could use for these quantum information processes. The problem is you have to do a lot of effort to try and protect it against this interaction with the environment and the loss of information by this so-called decoherence. Okay. So actually, Aspey's experiment was not done with electrons, which kind of interact very strongly with other atoms and other electrons that they might encounter along the route. It was actually done with light. Oops. It was done with light. And light also, like the electron, has a spin which can take two states. Light has something called polarization, which has two states. So the one you're probably familiar with is linear polarization. Your sunglasses are designed to only admit vertically polarized light and not horizontally polarized light, because the light that reflects off the surface of the road or the land tends to be polarized in the horizontal plane. So it cuts down the glare. But the more useful form of polarization of light is circular polarization, and there's two possible circular polarizations, right-handed or left-handed, and that's more like the spin up and spin down. And light can travel huge distances through empty space. You know, the light that's coming from the Big Bang, the early days of the universe, which I think you're going to hear a lot about next week if you come to some of those talks, has traveled ever since the beginning of the universe till it, or shortly after it, till it reaches us. And in fact, light can travel through fiber optics over large distances. So initially, these experiments were done first under Lake Geneva, then they were done under intercontinental cables, and the Chinese have gone into a big way into putting a lot of investment and into research in quantum information and quantum materials, and they actually have claimed to produce entangled states of photons between the ground and the geostationary satellite in orbit. So the EPR experiment, Einstein-Podolsky-Rosen thing, has actually been turned into, been practically demonstrated over large scales of distance now. So, as I said, around 1980, the condensed matter physicists were kind of arrogant enough to think they had a basic understanding of electronic and magnetic materials. But around that time, there were these two examples of weird properties were discovered which didn't seem to fit into the picture that had been developed. And actually, we now know that these two weird things are a new kind of condensed matter, quantum states of condensed matter, where the quantum entanglement was not just some small correction or small effect, it was actually central. So, because no one had been thinking about entanglement as a practical thing in states of matter, no one had thought about really clearly what entanglement could produce, okay, apart from chemical bonds, which were so obvious, right? And the two things, perhaps the most interesting one is the thing that Klaus von Klitzing discovered, the quantum Hall effect, which I'll come to. And I also found that, which is an unexpected experimental discovery. And I made an unexpected theoretical discovery. I think both of us were shocked to find the things that we found, because these were both discoveries that occurred not because we didn't know this stuff was out there, so we weren't out looking for it, but we stumbled across these interesting things en route and probably were wise enough to be able to recognize that this was something extraordinary. And that's the way most of the really big discoveries in science get made. Some things which take a long time to be, they're predicted a long time, like gravitational waves, and a lot of work is done to find them. But on the other hand, some of the other things in science are like unexpected discoveries that people kind of stumble into. And actually, I'll come back to a comment on that at the end of the talk. So anyway, after this, many more kinds of topological, what's now called topological quantum matter, have been discovered especially in the last 10 years or so, and which is why these early discoveries have led to new things, and developments in the last decade have really led to a tremendous amount of excitement about this, and really that's why this prize was awarded after so long, because it took so long for the thing to mature into something that so many people were working on. Okay, so what are these unexpected properties, right? Well, part of the excitement is that around 2000, Alexei Kitaev in Caltech pointed out that some of these new topological quantum matter systems could actually help to protect entanglement in quantum computing ideas. The basic difficulty in quantum information processing is protecting the entanglement you're trying to use as a resource, which is storing your information that you're processing from getting lost by interacting with the environment, and at least an intellectually coherent plan for how to use topological matter to protect the quantum information from decoherence came out of this thing, and that really led to, was again something that fed into the excitement in this field, that people felt, maybe this will help us get quantum information processing. Okay, so what is topological matter differs from, what is it? It differs from ordinary matter because it has entanglement properties that you can describe by whole numbers, numbers like 1, -2, -5, 4, etc. And states of matter which are described by whole numbers, different, they can't change smoothly into each other. You can't continuously go from a 1 to a 0. This thing's okay, so as I say, you can't change continuously from, for example, if there's a region where the matter is characterized by the number -2 here, and outside that, these little islands of -2, there's boring matter described by the number 0. There has to be a boundary between the two because it can't change continuously. And it turns out that often very interesting things start to happen on these boundaries between which have to be there where the topology, the number changes. And so, you know, that's a key property because that tells you the topological properties of materials can't change continuously. And that's quite different from the kind of what you need to do in current electronic technology, where all the computer chips are made out of these silicon wafers, which have to be produced in ultra clean rooms, where the workers are wearing all these white spacesuits, which are not there to protect them against anything poisonous on the chip. They're there to protect the chip from the little bits of hair and spit or whatever coming out onto the which will ruin them. So this stuff is very delicate, but if something has a topological property which is being used, that means that there's at least a small amount of dirt is not going to change it. You are not going to push yourself over the edge from -2 to 1 with a very tiny thing. There's some significant amount of disorder or dirt is needed before you ruin the properties, which is a kind of distinction to this clean room. So the classic example, what's topology? Well, the classic example in mathematics is actually the classification of a closed surface by the number of holes in it. And this has got a mathematical name called the genus, but it's really just a count of the number of holes. So if I have a ball, it could be a soccer ball, or it could be a rugby ball, or a cricket ball for that matter. And if I squeezed on it, certainly if I squeeze on the soccer ball, I could possibly deform it to look a bit like a rugby ball, but I'm not changing its topology. So if I put a little bit of pressure on the soccer ball, I will certainly put little indents in it on the side, and it will no longer be a perfect sphere if it was one to start with. But on the other hand, there's a big difference between the ball, which has 0 holes, and the bagel or donut shape, which has 1 hole in it. And holes come in, you know, whole units. You can't have 0.3 of a hole. There's either no hole or 1 hole. And so this apparently trivial discovery was actually the great discovery of this giant in mathematics, Gauss, who was a German mathematician around the beginning of the 19th century. And out of all the great discoveries he made in mathematics, he thought the most amazing and surprising one to him was something that a high school student can relate to. So in high school, if you have to pass all these exams you need to get into a good college, you probably have to memorize all kinds of formulas, including the formula 4 pi r squared as the surface of a sphere with radius r. And there's a sphere, of course, has a kind of the same curvature at all points on its surface, and curvature is actually measured by 2 radii of curvature. If you inscribe a sphere, a circle that way and another circle around it that way, on the sphere the 2 circles have equal radius. In the general case, at every point on a surface there are 2 radii of curvature, and the Gauss's curvature is a product 1 over r1 times r2. So on the sphere, that's 1 over r squared. So if I am told to do the integrate the Gaussian curvature over the surface of the sphere, I get 4 pi r squared times 1 over r squared is equal to 4 pi. And the formula is that 4 pi is 1 minus genus. The genus is 0. Another way to write it is 2 pi times the Euler characteristic, and the Euler characteristic of the sphere is 2. But as I say, this is apparently a very trivial result, but what Gauss discovered was that if I change it from being a sphere to a rugby ball, which is a problem that the smarter of the high school students might possibly be able to solve, the answer is still 4 pi. But if I take it and change it from a ball to a banana and start bending it around a lot, the answer, which would be a much, much more challenging mathematics homework problem for the high school student, the answer is still 4 pi. So Gauss discovered that as long as there are no holes made in the surface, whatever shape you bend it into, the answer is always 4 pi. Okay? And this leads to this example of coffee cups and bagels that the people at the Nobel press announcement made when they announced the Nobel Prizes. Someone was trying to explain to a very puzzled press, about donuts changing into coffee cups. But in fact, all the experimentalists who do work in this problem, they just love the fact that there's some mathematical basis to what they're doing, and they all go to YouTube and find a movie of a coffee cup changing continuously into a bagel and back again. Okay, so this is the integral of the curvature is 4 pi on the ball, and the mug with no handles with an inside and outside, it's still 4 pi. The bagel, it's 0. The curvature on the sphere is everywhere positive. The two circles you inscribe on the sphere they have radii pointing in the same direction. On the bagel, the curvature is positive on the outside, but on the inside, one of the circles goes that way and the other circle goes that way. So you get negative curvature. On the bagel, the regions of negative curvature on the inside hole exactly balance the regions of positive curvature on the outside. If I start to make more holes in the system, there's more regions of negative curvature. So this thing with 2 handles, there was, they called it the Swedish Pretzel, which actually, there's no such thing as a Swedish Pretzel. There's a thing called a Santa Lucia bun, but when they actually bake it, the holes get filled in. So that it's a fake, but this is the loving cup. This is the true pretzel. The German pretzel can be viewed as something with 3 holes in it. And this thing is called a loving cup. I'm not quite sure what this thing is called, but people have suggested that this could be the California loving cup. But anyway, let's move on. So as I say, mathematicians like to take a simple thing and make it much more abstract and more beautiful, but also more difficult for everyone else to understand. So the simple result of Gauss-Bonnet, this one here, which actually is called Gauss-Bonnet because Gauss didn't write it up with any details, and Mr. Bonnet went to the trouble of filling in the I's and dotting the T's, and so got his name on the theorem. So the Chinese mathematician at Harvard, or his American Chinese mathematician Chern, he turned this into a much more abstract formula by getting away from physical curvature over physical surfaces to a much more abstract curvature over abstract surfaces. And now mathematicians, unlike the physicists, the chemists, the biologists, and the economists, and even the peacemakers and writers, the mathematicians don't have a Nobel Prize. It's rumored that Nobel cut them out of the deal because his wife had an affair with a mathematician. That's the gossip anyway. And mathematicians are notoriously ageist. They kind of discriminate against age because they feel that anyone who's over 40 is totally past it. So they have a Nobel Prize-like medal called the Fields Medal, but too bad if you make your big discovery after 40, you're no good. So it's only available for people under 40. So that's been kind of corrected with a couple of medals. One's called the Rbol Medal, which is probably the more prestigious of the two of these, which you can get for your achievements during your life, which are not just restricted to under 40. And the other one is the Chern Medal, and there sitting on the thing is the Gauss-Bonnet Chern formula on the back of it. Okay. So, what did I discover? Around about 1981, I was kind of playing around. My thesis topic was on magnetic impurities in metals and valence fluctuations, some kind of properties of electronic properties of metals. And I came up with a new way to look at some of these states. And at some point, I realized that the methods I had used could be used to take a new look at some problems in magnetism. And often you kind of learn something. In science, there's a great amount of unity in physics. Things which are applicable in one area turn out to be applicable in an apparently very different area, probably because the same basic principles of quantum mechanics are kind of applied both to elementary particles, the Big Bang, God knows what, and cold electrons. Yeah, so I was looking at a problem in magnetism, which wasn't really my area, from a different viewpoint. And if you're looking down into a valley from two different mountain peaks, you may see something different on your peak from what other people have been looking at it from the other peak. So looking at the same problem from different points of view is an incredibly fruitful thing to do in science, because you can learn about the same thing in fact, it's very good to have many different explanations or versions of the explanation of something, so you can take different points of view to explain the same thing and see how they all can come together. So the usual view of magnetism was the following. There were a magnetic atom. In this case, it's a spin 1 magnet, which just meant that the atoms with a single spin is identified as spin 1/2. So 2 of these is spin 1, 3 spins would pointed in the same direction be spin 3/2, 4 spin 2, etc. So different atoms have different amounts of spin on them. And the nickel atom in particular has a spin 1 state. It's got 2 electrons in a d orbital like to be parallel to each other. But the view of magnetism is that at the time was that you can, standard magnetism, just assemble a load of little atoms. Now, if the spins are all pointing up in the same direction, this is a ferromagnet, and you can use it to pick up a paperclip. And that kind of magnet is very obvious because, you hold them together and they push each other apart, they pick up paperclips. There's a less obvious kind of magnet, or magnetism, where the atoms are pointing alternatively up or down, or sideways, right and left, it doesn't matter. They can be different. Those are different states of the magnet. But it won't pick up a paperclip because the magnetic effect of these on a paperclip will be cancelled by the magnetic effect of the others. But nevertheless, it's a magnetic state. And to make this typical kind of magnetic state, there's really nothing special gluing the atoms together. You could just bring these magnetic atoms and stack them up in a row, up, down, up, down, up, down. And there's nothing, if you try to cut the thing in half down the middle, you could separate it. You wouldn't be breaking anything when you separated it. Well, it turned out what I discovered, but from taking looking at this old problem from a new viewpoint, I discovered a state which I didn't draw this picture at the time, but this is a picture that other people draw after me, but it was a very clear picture of the state I found. It's a state where these two, instead of the 2 spins on each atom, staying glued together and pointing in the same direction, the thing splits up, and one of the 2 joins with the other one in this up, down, down, up chemical bond-like structure, which is entangled. And you see that the joining this one with that one in an entangled state forms this thing which is like a little bond. And if I try to cut this in half, I've got to break the one here. Now, that leaves a very simple principle that there's going to be one spin. If I join this with that, there's 1 spin left over at the end here and 1 spin left over at the end here. So the structure you get has got this property here, and it's got a very typical property of topological states, that there's something funny at the end. So if I continue this by putting the regular kind of magnetism to the other side, there would still be at the boundary between entangled and non-entangled, there'd still be this extra one floating around. And this is an example of the fact that you typically find something at the edge of these topological states. So anyway, this was very shocking to people in the magnetism community. It probably, it was actually very good for me. I probably didn't explain my ideas clearly enough because they were initially denounced very, I was amazed at the amount of anger they elicited. I was actually denounced by some senior person, got up at some meeting and said this is utter nonsense. And my paper was rejected. I mean, I started off by saying it's a physical review letters. The last one that rejected it was Zeitschrift for Physik B, so I was kind of moving down the food tree, right? It probably went to the same referees at each time. Eventually, I rewrote the thing in a much more different way, and when I understood it more clearly, so it was probably my fault for not kind of expressing myself clearly enough. But anyway, it was a kind of surprising thing that you, again, I suppose is something different from the way unexpected shows up. You know, there should be some resistance to changing one's ideas because most of the crazy stuff you hear about really is crazy and is nonsense, right? So there has to be some resistance to change. But anyway, the basic thing is that science is not a philosophical discussion about politics or religion or anything, where it's actually in the final analysis, arguments in science can be settled by experiment. And in fact, indeed in this area, experiments have been made possible by huge advances in material science, where people can actually, very clever material scientists have learned how to make some of the kind of toy models that the theorists have devised to illustrate new principles. And in fact, as I say, the fact this idea was, prediction was controversial, actually led to development of a whole lot of new techniques, both experimental and theoretical, because people love a controversy. So people came up with ways to weigh in on one side of the controversy or the other and develop various new techniques. Experimentalists, of course, they would love to prove something wrong. That's their first. Experiments love to prove a theorist wrong, but if they can't prove them wrong, the second best is to prove them right, which is also good. So it's kind of there was a lot of stuff going on, but in fact, because of this strong attack, it was very good for my career, because having had people very strongly denounce this as wrong and the experiment proving it was right, then there were two possibilities, you know, either they were stupid or I was whatever. You know, so it was very good in the finally after this was all settled, it was very good for me. So the analogy of this thing is actually this state is somewhat analogous. I mean, to a chain of people, if you have someone who's not been injured, at least, arms generally come in pairs. So a person has two arms. But on the other hand, if I have a line of people and they all join hands, they're somehow, the freedom of their arm is being removed on the one they've joined hands with, and there's this chain of people. But at each end of the chain, there's one arm that's free to wave around and do what it wants. So you've apparently violated the thing that locally arms come in pairs. And this is we'll see this again in the attempts that Microsoft are doing to make a topologically protected computer. The same kind of image of a chain of people with something left over at the end is important. Well, this state here, I mean, it looks kind of pretty toy model and, you know, what's the big deal? But the big deal was only that it turned out to be the first and the simplest example of this new kind of topological states. Some of the others are much more extraordinary and do much more interesting things. But anyway, in this, there's recently been a big classification of this, and this is somehow like the hydrogen atom of topological states. You can't get simpler than that. Of course, all other atoms are much more complicated than the hydrogen atom, but the hydrogen atom is perhaps the simplest one that you can actually understand in great detail, and this is what this role this one played was. So they put it in this whole picture, which is actually somebody else's, the Affleck Kennedy Lieb Tasaki picture of my state got ended up on my Nobel certificate. There is the entanglement, the up, down, minus down, up thing. These everyone that each year they put they have a separate theme. The theme in that year's thing was doors opening to a hidden world, and all the people in physics getting a prize. They got a picture like this with something, something adapted to their individual work behind the door. Okay, so what about the other important discovery of the period? That was the quantum Hall effect. And there's Klaus von Klitzing holding his medal. The quantum Hall effect is actually is to do with electrons moving in a magnetic field. Magnetic field deviates. Electrons don't move in a straight line if there's a magnetic field attached to them. The magnetic force on the charge makes it want to go around in a little circle. And the Hall effect is something that actually, if you do a little bit of electricity, you learn about the Hall effect, because it's the effect that allows you to know that electrons are moving in a metal and not the charges that actually move in the electrical wire are actually negative charges. Well, if you take what's called the classical Hall effect and plot the voltage measured across this wire as a function of magnetic field, it should go in a straight line. There should be a kind of 45-degree line here. But at very low temperatures, when the quantum mechanics kicks in, this kind of slope of 45 degrees gets turned into a staircase. And the amazing thing was that the value of on these staircases, on these plateaus, is incredibly accurately given. In fact, it's 1 over this thing, but it corresponds to a whole conductance of a whole number times these very fundamental numbers, E squared, the charge electron squared, divided by Planck's constant, the fundamental quantum constant. And this is actually, although it wasn't really appreciated at the time, this could only be an effect of topology. Okay, so this is the physics is being controlled by a whole number. And actually, this is actually about a few weeks ago, at the end of November, middle of November, this finally has introduced democracy into the system of weights and measures, right? So if you went into the marketplace and you wanted to buy a kilogram of bindi or something like that, you might suspect that the dealer in the market was swindling you and was using a bad weight. But if you wanted to contest that, all you could eventually do, finally, you could take it to compare it. The final analysis, the only way to check would be to take a plane to Paris, take his kilogram with you, knock on the door of the Bureau of Standards in Paris, set up by Napoleon when he authorized the metric system to be created, and beg them to allow you to take a look at the one they have in the safe in their basement. Because the kilogram used to be based on a lump of metal that was kept in a locked safe at the bottom of the building in Paris. But we've actually replaced this old system of the kilogram with a modern system where the weight, where the quantum Hall effect and another quantum effect, the Josephson effect, are together used to weigh the system. And they now can make a device called a Kibble balance, which now anyone can build it. So the Bureau of Standards in New Delhi can build their own Kibble balance, and they can test the dodgy market dealer scale directly without having to fly to Paris. So anyone can now build their own weighing machine tester and check and have their standard for the kilogram. So it's now based on fundamental principles which turn out to be the ones which made this thing called the quantum Hall effect work. So the topological nature of the quantum Hall effect took quite a bit of time to become clear. The electrons in this magnetic field in the interior of this sample, they're pinned to a little two-dimensional surface, a little layer in a gallium arsenide device. But in the interior, they're going around in little circles, and things which go around in a circle or have a periodic motion in quantum mechanics, they get a kind of, their energy is fixed to be a multiple of a certain basic energy associated with the frequency of the rotation. And so the energy levels in the bulk, they all take fixed values. Now the magnetic field has split the spin degeneracy, so the spins are kind of aligned or anti-aligned with the magnetic field, so you can only put one electron in each orbital because the spin has already been used up. And the thing is, the electrons that are close to the edge, they don't get to complete their little circle, because once they hit the edge, they actually bounce. And you can see that if they want to go around in a clockwise direction, the ones that hit the edge are going to go bounce, bounce, bounce in an anti-clockwise direction around the edge. And this is very typical of a topological system, where there's something funny at the edge, and there's something really funny here because it allows signals to travel in one direction only around the edge, okay? And the direction, of course, is set by the magnetic field. So if I fill this up, since you only can put one electron in each orbital, there's some highest orbital that's occupied in the ground state, and there's a lowest one that's empty, and the difference between those two is called the Fermi level. But basically, provided as I change the magnetic field, the number of levels down here changes. But so long as the Fermi level is somewhere in between here, which happens for a range of magnetic fields, I will get this effect of a gap in the bulk. And this means that you don't have to fine-tune the system. The amazing thing that von Klitzing did, oops, let's go back. Von Klitzing's experiment was also a lucky break, because what he did was he set up a current flowing in his wire with a constant current generator, shoved it in the magnetic in the magnet, and switched the magnet on. So the thing is, when you switch the magnet on, it's never going to come to exactly the same field every time you do it. But because of the way he organized the experiment, the answer, the readout on his voltmeter doesn't depend on precisely on which field you get. It just had to be somewhere in this range set by having the Fermi level in this gap. So he found that the digital output of his voltage measuring device was the same to a number of significant figures each time, 4 or 5 significant figures. Of course, his first thought would be that, this has to be a broken voltmeter, right, or something like that. There has to be something wrong with the measuring thing. But he finally convinced himself it was a real effect, and it was something unheard of in condensed matter. You do a measurement on some dirty old sample, and you get this number that's precisely repeatable every time you do it. Now, if he'd chosen to do the experiment the other way, by putting the sample in the magnetic field and then switching on the current, you'd have never got the same current every time, and you'd have never got the same readout on the voltmeter every time, so he wouldn't have noticed it. And in fact, people had done the same experiment before him, but they did it that other way, and of course they never noticed anything because no one was expecting this effect to be there. It was only the dramatic effect of seeing the same number to 4 or 5 decimal places coming out every time that kind of alerted him to something amazing was going on. And okay, so it took some time to see topology in this thing, and these fellows, one of whom, David Fowlis, got the Nobel Prize as a co-laureate of mine. They did some toy model calculations that theorists like to do. The real system has a lot of. Let's go backwards. The real system actually has dirt inside the region, so it's not as clean as this little picture I drew here. The thing is, it's kind of up and down inside the region, so it's a bit more complicated than what I said. But they replaced the dirty system with a completely physically unrealistic system by having a nice little periodic wavy potential inside, which has nothing connected to the real physics, but is something you could actually do a calculation with. And they discovered this kind of crazy formula over here, which basically predicted that the whole conductance was indeed remained to be e squared over h times this number here, this object here, which has to be an integer, and they didn't understand why. But around that time, another amazing discovery, which I'm not going to describe, Michael Berry discovered something called Berry's phase, which was a simple thing that had been possibly seen before, but not really noticed as a general principle of quantum mechanics before Michael Berry, that's now really central to a lot of this new thinking about quantum mechanics. Discovered something called Berry's phases, and this fellow here, a mathematical physicist, he got told about, somebody told him about Fowlis's formula, and someone else told him about Berry's formula, and when he took a look at this thing, he realized, my gosh, this is exactly Chern's formula, the Chern version of Gauss-Bonnet. So the fact it took a different kind of people to recognize that this was anything connected to this deep mathematical principle related to coffee cups and donuts. In fact, the donut is in a very abstract way present. It's something called the Brougham zone of this system is topologically equivalent to a donut. So that's where the donuts come in. Okay, so part of that was, so they discovered this formula, and the quantum Hall effect was very, very interesting, but it seemed to be something associated with huge magnetic fields and the particles going around in little circles and everything, and even in the Fowler thing involved a little wiggly potential in a huge magnetic field. And of course, in retrospect, it's probably obvious, but in 1988, I realized that the basic principle wasn't the magnetic field. The basic principle was something called broken time reversal symmetry, which means that if I look at a movie of something, I can see whether time was going forwards or backwards. In the magnetic field case, it's because the electrons go around in one direction. If you reverse the direction of the film, they will be going around the opposite direction. But you can get broken time reversal invariance with a ferromagnet, with a magnet rather than just a simple magnet and not a huge magnetic field. And in fact, you can get this quantum Hall effect in a rather ordinary crystal setting with as a consequence of ferromagnetism. And in fact, at the time, I wrote this paper which came out of a realization that came out of just an argument about whether the magnetic field or the time reversal was the key aspect of all this. Oops, sorry. And in fact, at the time, I proposed a toy model. Again, toy models are incredibly useful because you can actually do calculations with them. This was actually like a single sheet of graphite, which we now call graphene. And at the time in the paper, I said, well, this toy model is basically implemented as a single sheet of graphene, but of course, no one will be able to make such a thing. But of course, the power of Scotch tape to actually make graphene only became known and also led to a Nobel Prize, 15 years later. But anyway, so replacing this magnetic field thing with a much more standard model of solids, then this actually led to the topological insulators, which were the subject of this recent developments. And these chaps, Charles Kane and Jim Lee, took 2 copies of my little toy model there and stuck them together to make another toy model. Said it was due to now that you've got spin up moving one way around the edge and spin down moving the other way. So this one is actually time reversal invariant. But they found out that this shouldn't work. If you make this dirty, this should not work according to Chern's principle. So actually, I had tried this model too, but I never bothered to do the calculation because obviously when you make it dirty, the Chern's number will break. But it turns out this thing is protected by a new kind of topological protection, which is not there, which survives breaking the Chern number. So it was a big surprise to everyone, them, and this thing led to a 3-dimensional version. The others were all on 2-dimensional sheets. And then people discovered that in their laboratory, sitting on their laboratory shelves, they had topological material all over the place, and they'd never noticed it because no one had ever looked on the surface of these materials. Again, if you don't know something's out there, you're not going to go out looking for it, and it will really relies on someone accidentally finding it one way or the other. Because if anyone expected it, anything that was expected, someone would have already looked and found it, right? So again, it turned out that these topological 3-dimensional materials had these topological orders, and you just had to look carefully at their surfaces to identify which ones they were, and people hoped to do interesting things with them. Okay, so in fact, the original one that I found, it was a toy model, and in the end, it may take a long time for people to work out how to make these things in real materials. And in fact, this is an example of how China is progressing. China is putting a huge amount of money into experimental condensed matter research, especially involved in quantum materials and things. So maybe I think it'd be very good if India kind of keeps up, manages to also stay in this game. So I think it's an important place for the future technology. But essentially, they made the thing, this kind of thing, the ferromagnetism, you need to put a tiny magnetic field to make the ferromagnet order, but basically it's much more convenient to do stuff with things not in high magnetic fields, and you get really interesting things if you stick superconductors on top of these things, and superconductors really don't like magnetic fields, so a lot of interesting possibilities have opened up by actually finally creating this material, making these samples. So, what's this good for? In fact, by having one-way transporter on the edges, you've actually, you've done what's done on the roads, right? This is the archetypal picture of separating the cars moving on the left and the right, and this is actually the British or Indian road, I can see from the direction of the lights. And so in a normal metal, the electrons, there's more when a current flows, there's slightly more electrons moving one way than the other way, but there's a lot of electrons moving in all directions, and they're all going jumbling around. And clearly, you can get some more efficient form of transport if you can separate the ones going one way from the ones going the other way. And people hope to be able to do something with this interesting aspect of topological things. And in fact, principles in physics have applications, way beyond the original place they were first found, because it turns out you can do this thing with light too. I mean, it's not really the same, it's not really in the light, it's not really got a direct interpretation in terms of entanglement, but and it's not quite as full as it doesn't exhibit the Hall effect as the electron systems do, but you can still get the same topological principles to cause light to flow in a photonic crystal in one direction only, and if the light is flowing along the top surface in one direction, and you put and you put an obstacle in its way, if it's not possible for it to be reflected back, all it can do is kind of creep around the obstacle, come around and go back on its way. So it's a very interesting thing. So finally, let's have a look a bit more. So quickly, the integer quantum Hall effect was soon followed by a much bigger puzzle, the fractional Hall effect, which also led to a Nobel Prize. Now, you can only get, only 3 people can get a Nobel Prize, so the theorist who came up with this amazing wave function, which I won't describe, but is a very amazingly simple thing, and he found it by accident too, by playing around with a 3-particle calculation. These guys found the measurements soon after the integer Hall effect was discovered, and people had convinced themselves it was true, and the value, there had to be a simple whole number multiplying e squared over h. This one found out that it was a 1/3, a fraction, a simple fraction multiplying e squared over h, and that was very unexplained and took a long time until this was discovered. Was a huge puzzle. This is the man who actually made the Art Gossard at Bell Labs, made the sample, and you can see from this how forgiving topology is, right? This sample, put it this way, if you show this as an example of your soldering work, you wouldn't get a job at Intel, right? But anyway, so this thing showed up the topological effect, and it led to various things, but the quantum computing aspect of this emerged even a bit further. This is something called the abelian quantum Hall states. Another mathematical term, non-abelian ones followed, and those are the ones that turn out to be theoretically useful for supporting something called universal quantum computing, which is the holy grail of the quantum computing community. And these fellows, Greg Moore and Nick Reed, came up with this non-abelian states. Alex Kitaev actually launched this whole thing by pointing out around the year 2000 that this would actually be useful in principle for quantum computing. And the way the information is somehow stored, these are little vortices, I'll show what they are in a minute, but the information is somehow stored in the configuration of between the vortices, and you braid them around each other like braiding hair, and you're processing the information. And in fact, there's 1 qubit for every 2 of these little blobs here. So this is actually something like a little the device is something like a little whirlpools, little vortices and whirlpools in this quantum fluid, and and so there's an edge mode going. There's one-way transport around the edge outside. These are like little edges inside, so there's little transport going around in the opposite direction. But when you make these things, you make them by pulling a bigger one of these things, splitting a double one of these things into two, and then you actually move them around each other to do the braiding. There's some sequence, so the coding pattern would be the sequence you move these around each other. And the thing about quantum computing, at least theoretically, if you want to find the best way, the best path, something called a traveling salesman problem, for example, the best way to choose a route between a number of cities, visiting them all on the same thing. The only way to do it in a classical computer is to go through all possibilities one by one and find out which is the shortest. The idea, the idea that's sold, at least in quantum computing, is in some sense the quantum calculation does all the calculations in parallel at the same time and smells out the right one. So it's a kind of testing all possible. So it's somehow like quantum computing is, in principle, something like a massively parallel approach to the problem, because I haven't really got the time to explain the issue of quantum mechanics, but that's the way it goes. Okay. So in fact, where's the information hidden? In this particular example, we've got four of these vortices rather, and this is enough to, this actually contains one qubit. And so the vortices are exactly the same positions, and by looking at it I can just see the vortices are, but in fact the history of how they were made leaves a kind of trail of entanglement between them. So if this one is entangled with that one and this one is entangled with that one, it means that the qubit might be pointing in the up direction, and if the entanglement was this way, it might be pointing in the sideways direction. And by pulling one of these around to the others, I kind of mix up and spread the quantum information around in a different way, and the processing is doing that way. So that's somehow the toy model for exactly where the information is. And in fact, if you try to look at this is actually a calculation of the two possible states. This is again a system with these four vortices stuck in fixed positions, and this is showing the up state of the qubit and the down state of the qubit. Say, if you look very carefully, you can see there's slightly different wiggly, wavy patterns in the electron density in between these little vortices. And if you could study them carefully enough, you could tell that this one was the up state and that one was the down state. And if I took a sideways state, which would be a linear combination of those two, I would get patterns which are somehow a mixture of that. But these are very, very tiny little ripples, and if I were to pull these things apart further, the ripples get tinier and tinier and become completely imperceptible, and that's how the quantum information gets hidden when the vortices are moved far apart from each other. And then you do this processing by braiding them around, bring them back together to measure it and things. So this is the story that's being sold to the technologists, at least. And in fact, as I say, this is a kind of beautiful dream. It's intellectually satisfying answer to scalability and robustness against decoherence. Of course, you know, I'm not telling you to go out and invest in a quantum computing company. I mean, if you do, that's your decision. I'm not taking the risk to advise you, but you know, entrepreneurs and physicists, of course, have beautiful dreams and they get very attached to them. Technologists and entrepreneurs who are deciding what to do have to kind of look at these things more skeptically, of course, and make their decisions. But and of course, fusion power is certainly an intellectually satisfying solution to the world's power needs, but it's been promised and been taking a long time coming. So, but I personally do believe that we're going to see some interesting technologies coming out of all this new work in quantum matter and quantum information. So, as I said, Microsoft have gone into something called Majorana zero modes. central idea of the effort, there may be some better versions coming out of Microsoft, which is a two-dimensional thing. But the rumor is they put $1 billion into it. I don't know how much of that is true, but they have not achieved the braiding needed yet. But so it's again one of these promised things which are taking longer than expected to come. But the braiding idea is I'm going to finish on this thing. The braiding idea is very similar to the comes out of something very similar to this original spin chain thing. You put an indium arsenide nanowire, a very tiny little crystal of indium arsenide that grows in an amazing way out of like a hair. So they're quite easy to grow, it turns out, in this long configuration. It's put on the surface of a superconductor and some magnetic fields applied to it. So there's the little indium arsenide wire, 1D wire, and there's the superconductor it's attached to, and it's got something called spin-orbit coupling, which is large. And but the actual principle behind it is, again, very simple topological principle that essentially, in the presence of the superconductor, the electron state of the standard electron states in the presence of a superconductor kind of split into two things called Majorana states. So the standard electron somehow splits into two things, two Majoranas, and then the interaction with the superconductor kind of causes them to rearrange themselves, and they reform new electron states where the purple and the green one are formed by aligning with the neighbors, and again that leaves one thing left over at either end of the chain, which is this Majorana zero mode. So you again get back to this picture of the chain of people holding hands, and now the thing at the end is not the free spin, but the Majorana zero mode, which contains a lot of interesting entanglement along the chain, and you're tending to do some braiding. It's along a chain, so that the braiding protocol for this is something like you need a T-junction in the chain. It's something like a model toy train set, and you have to move these things around in a complicated way. But I think it's going to get better schemes are going to come out. The people have actually claimed to have seen the Majorana zero modes at the end of the chain, and they're still controversial, and we're still waiting for braiding, but it's there. But in fact, this is just one of the many approaches which people are trying for quantum computers. There are things called transmon qubits. There's stuff going on I saw at IISc. That's nitrogen vacancies in diamond qubits. Ion traps are perhaps the best one. All these are very interesting qubits. They don't have the obvious scalability as a topologically protected one would have, but they may actually. But I think the ion traps are probably the best ones at the moment, and the claim is that the claim is you just need 50 qubits to get something called quantum supremacy, where the computer would be better than a current classical computer, but right now they're on the much smaller numbers of qubits, of course. So actually, I don't know where this is going, but I'm pretty in detail. But as I say, by all this huge effort that's going on in this area, I'm sure we're bound to learn lots of new things, and some new technological possibilities are going to come out of all this. And finally, yeah, so the moral in all this was that toy models, which is my speciality, is something that's been very, very important in the thing, because it provides simplified pictures where you can actually see what's going on and kind of have a cartoon of the physics you're trying to find. Underlying all this stuff is probably very deep mathematical stuff, like the Chern-Gauss-Bonnet theorem, and now all kinds of things called cohomology and cobordism that people are talking. So a lot of fancy mathematics, and of course the really key thing is the people who actually managed to make this stuff turn it from kind of theorist dreams into at least a reality. And the interaction of all these different communities who probably find it difficult to understand each other when they talk has been crucial. So finally, here's my motivational message. So, people ask, how could I get a Nobel Prize? Well, the thing is, the basic thing to get a Nobel Prize, in my opinion, is luck. Because you could be a super genius. Of course, Einstein is, of course, the counterexample, right? you can be one of these super geniuses, and once something comes along, you can maybe sort out all the details and explain it incredibly well and find out all the things. But there's a certain amount of luck to stumble across something that no one expects to be there. Again, there's this principle: if no one knows it's out there, no one's out looking for it, and so that's the chance. Of course, to actually, when you stumble across the two things I described, which why I stumbled about, I was truly shocked each time I found these things, and I'm sure von Klitzing was shocked and other people were. Of course, you need to have luck to actually wander towards something which no one knows is there. You, of course, have to have the preparation beforehand, which enables you to recognize that you've found something, because otherwise you can be, walking along the path, kicking the dust, and if you're not looking at your feet, you might not have noticed you just unearthed a huge big diamond. You walk on past, and of course someone else is going to come afterwards and pick it up, right? So you need the preparation. It's not obvious when you first find something what it is, right? It often takes time for the significance or non-significance of something to become clear, and often if you actually do find something new, there's probably a lot of resistance, and you need commitment, and you probably need kind of, you need to be committed basically to science in some way. You need to help you go through the bad parts and fight for things. But actually, these are the typical any kind of inspirational speaker, whether it's telling you about success in business or not, is basically giving you the same kind of message, but it's probably true, right? You need that. So finally, as scientists, we kind of need to get people to, give us money to keep. Theorists used to be cheap. They just needed a piece of paper and a pencil, but actually the experimental aspect of all this is absolutely crucial, that you actually need to show things are real. So we actually do need to, go out and convince politicians. I had tea with Mr. Modi a couple of days ago, and hope I was able to give some advice. But anyway, basically, one of our roles is we have to go and explain ourselves, hopefully in a non-technical way, to outreach politicians and public. And this is me supposedly explaining Chern-Simons theory and flux attachment in the quantum Hall effect to a political person, or non-political person, perhaps. Thank you.
If you have questions, please raise your hand. If you have questions, please raise your hand. Okay. There's one there.
I have heard that the impurities play a very important role in the observation of integer quantum Hall effect. Can you make a comment on that?
Sorry, can you repeat the question? Or something?
I have heard that impurities play an important role in the observation of integer quantum Hall effect.
The impurities play an important role in observation of quantum Hall effect.
Yeah, well, the impurities, the real system has impurities, and they play some role in causing the plateaus to be there, or in causing in changing a straight a slope into plateaus. The real system has impurities, and but I think it's very difficult to. People spent a lot of time worrying about impurities in the integer Hall effect, and in the end, you can explain the effect on a topological basis, and even with impurities, finally it's a topological explanation. What Professor Salas did, he had the inspired idea to replace the real problem of a kind of jig-jaggy, dirty potential with a kind of simple sine wave, There's something you could actually calculate with to kind of stop the, to cause the electrons to, some electrons to sort of not slide completely with a magnetic field. If the system allowed everything just to slide sideways, you would actually not see the plateaus. So you need something to kind of prevent the normal electrons from sliding too, and just see the condensed electrons from sliding. So yeah, so it was, but in retrospect, one should have, the fact that the edge modes were there was seen early, but in retrospect, one would say it was kind of obvious from the beginning it had to be topological. It had all the hallmarks of it, but at the time, people weren't even thinking in terms of topology, right? And in fact, the first time that topology came into it was when the mathematician Barry Simon recognized Thoules's formula was just the Chern sign, the Gauss-Bonnet Chern formula, right? So the word topology really hadn't even emerged in that field until that point. And you know, and now of course there's a huge amount of much more complicated states and interesting states, and a lot of mathematics behind it now, and people are using topology right, left, and center. But no one in this area knew that topology had anything. There would be any kind of interplay between topology and quantum mechanics, really. And so, yeah. But in fact, you can understand you need the impurity, the dirty system with random impurities also based on it. It's also topological, yeah.
In your analogy of people holding hands, does the topology infer that it's a sort of wire that transmits entanglement along multiple particles? So if I change the spin at one end, the spin would be the opposite at the other end?
It's not that, no, but I guess the metaphor of the holding hands was that, as I say, if you think about the chain of people holding hands, right? There's one free hand at each end of the chain, right? Suppose someone breaks the chain by forcing two people in the middle to unlink their hands, right? Now you'll find you've got two chains, and again, each chain has a free hand at either end. It's a bit like, it's not exactly the same, but it's a bit like trying to break a bar magnet in half to get a north pole. You've got your north pole and your south pole, and say, I'd like to break it in half and keep the north pole, but once by itself. But once you've broken it in half at the break, you automatically got another south pole. And when this topological state is there, you can't avoid, when you break it, you can't avoid having a free hand or a free spin at the end of the system, and that's the topological principle. So you have a row of people, the ones which are up to this point they're not holding hands, above the other point they're holding hands. I guess if the people who are not holding hands have their hands clasped together like that, right? There's the one in the at the break. There's the boundary between the normal and the entangled. There's one free hand floating around, and so. Yeah, that's actually one of the hallmark signatures of the topological states. That's not the only signature, and it's something unusual at the boundary. Yeah.
So thanks for that beautiful lecture, but when can science see a perfect marriage of relativity and quantum mechanics theoretically or practically?
Well, okay, the issue is not so much relativity, but gravity, right? So special relativity has been, perfectly adapted to quantum mechanics. I mean, Dirac's equation basically solved that problem back in the last of the four heroes of the one in 1932. No, the big problem, we don't understand how gravity is formulated by Einstein in terms of the geometry of space-time. The quantum version of that implies that, well, quantum things are fluctuating, so that means the geometry of space-time has to be fluctuating. The so this is what string theorists were trying to do. String theorists probably all seem to be working on black holes these days, but there's also ideas of that space-time itself may be held together with entanglement. You know, space-time, it may not be a continuum, but maybe entanglement of things. But these are all kind of, no one actually knows, and people are, you know, trying to find out. No, this whole answer about free will, you know, am I preordained? Is what I do completely fixed by the initial conditions of the universe? I mean, these are all very difficult questions, right? One can only kind of hope to work on a kind of small part of practical questions, and a lot of people are putting a lot of effort into trying to grope their way towards a quantum theory of gravity or quantum theory of geometry of space-time, because we believe that way back to understand the Big Bang or whatever happened before inflation, you know, things like the ultimate fate of the universe and all this, we need to understand. We can only look back so far, but you know, people hoping to find something, and that's where people might, if quantum mechanics, most people believe that quantum mechanics principles should hold for gravity too. Hawking famously said no, and there was this whole quantum information paradox of black holes and the famous bet with Kip Thorne. But we kind of believe that quantum mechanics should be meshed with gravity, but then, you know, we'll find out what actually happens. I mean, if quantum mechanics is to break down, will it break down in the center of black holes, or who knows, right? These are all very challenging, but these are actually difficult questions. Then the main difficulty which I would find with those is there's no experimental, or almost, it's very difficult to come up with an experimental guide for where to go. And in fact, I had I had to make a choice. I got accepted to stay on at Cambridge as a graduate student. I had the choice to work either with Mike Green or Phil Anderson, two people who'd given half of a very influential lecture course, which influenced me on modern quantum mechanics or advanced quantum mechanics. The two possibilities I had was to work on string theory, but this was back in 1973, when string theory was supposed to be a theory of the hadrons, and the other one was Anderson working on stuff to do with condensed matter. I went with Anderson, partly because I found it more concrete. It was actually working with, you know, you could somehow visualize the real materials or what you were trying to do. And that version of string theory died 6 months later. It was based on something called the MIT bag model for strings, which was shown to be unstable, and string theory went into a wilderness until people thought, well, it might be not a theory of the hadrons, it might be a theory of gravity. But, you know, my career would have, I wouldn't be here if I'd chosen the other way. So it shows that when you're kind of a graduate student, you're faced with choices, you don't know the significance of them, and you just have to make them and do the best you can, right? And but yeah, it's obviously I would vote for going with the more concrete problem. Lots of people are very inspired by, you know, the problem of, you know, of completing Einstein's task or something like that, and finding out, you know, quantum mechanics and space-time. You know, both kinds of work is needed, but yeah, it's an inspiring but difficult question, and I go for the quantum, the more mundane things, which are also cool. Yeah. Yeah, yeah.
If you get sort of -2 or +5 or some number which
Yeah.
has a region in the topological space. So how do you describe that with entanglement? What do you?
Well, actually, the topology is somehow, what's being involved is really the topology of entanglement in the system. Okay, so there's some topology. Something is topology. You classify it by whole numbers, right? And you can. So there's a kind of. It may be an infinite set of possibilities. There may be -1 to plus infinity or something like that, or the fractions. But the topology is really a classification of some kind of the way the entanglement is kind of arranged in some sense, right? And the different states are like somehow different arrangements of entanglement in some general sense. So that's where the topology is. And before we actually thought about entanglement as a property of matter, we actually didn't really realize that quantum states had to be classified, that there were different possible states that couldn't transform into them. Basically, if you're two states which are topologically distinct, they cannot smoothly transform into each other, right? You cannot smoothly transform the soccer ball into the donut. At some point, you have to stick your fist through it and break it. And so, in the quantum case, usually the simplest topological states have some kind of energy gap which protects them, and they can only transfer to another state if the energy gap closes and then reopens, and that's a kind of phase transition at which the topology changes. So, but yeah, as I say, it was totally not really obvious. Topology had been thought of in condensation. People in liquid crystals had thought about classical physics, had thought about topology in the shapes of different kind of defects in liquid crystals and things, and that's much more like the Gauss-Bonnet topology of surfaces and things. The quantum mechanics was much more abstract, and it took this kind of connection with Chern to see, that this was topology too. Yeah. Okay.
So the discussion about all antisymmetrized states are not essentially entangled. What is your comment about that? I mean, essentially when we say two states are entangled, you essentially cannot write them as a product state. So if you write any antisymmetrization state, which is essentially not, you cannot, that means any two fermions in the world are entangled. So that doesn't mean that all are entangled. So what is your comment about that?
If you measure the system is entangled, two systems are entangled if a measurement on one system has an effect on the other one. So quantum, when you measure something, you either get one thing or the other thing out. You destroy some information. Once you've measured the state, you know what it is, and you can't copy the state anymore, right? You can't recreate it. You can try to make another state the same way, but once you've measured it, you've lost it. So two things are entangled if a measurement. Two things are not entangled if you can measure something on one subsystem without affecting the other one. And your comment: are all electrons in the world entangled because of the Pauli principle? It's really the spin. The Pauli principle doesn't tell you what their spin directions are, right? The state of the electron is actually, the entanglement is not so much the anti-symmetry, but the fact that one electron is up, the other one is down. You could put the electrons in an anti-symmetric state when they're both up. The wave function just has to have a node in the middle, and you can make a perfectly well-entangled state of two upspin electrons, right? But they're entangled spatially, not by their spins, right? The chemical bond thing, it's the spins that are entangled, yeah.
Maybe very quickly.
Coming back to that hand-holding analogy, I mean, you told that it doesn't really imply that the hands are just wiggling. I mean, there are loose ends on the chain. So is it true? I mean, is it correct way to interpret this as the two hands, the wiggling hands are like entangled or something? I mean, as in they are correlated in some way, the length scale of the chain.
Actually, the two spins themselves are at the end. themselves entangled, right? What it's the things along the middle of the chain are entangled, along the bonds. So, okay, it's a slightly, not imperfect analogy, but the basic thing is that if I join these things up, if I take something apart and join it up in a different way, and I leave something behind, those things can't go away by themselves, right? So for example, the Majorana zero modes, that's actually half of a fermion. In some sense, you've divided a electron state into two halves and made them spatially separated. So if I put an electron, the electron can only go into a linear combination of those two Majorana zero modes. So if I add an electron into that one, it's actually the state I've made the electron is also added partially in the other one. Right? If I add an electron to that system, it's a linear combination of both states. It's complicated, right? But sorry.
Chain is enabling the entanglement. It is what it. The chain is enabling the entanglement. That is what it is. I mean, the bonds are enabling the entanglement.
In the Majorana zero mode case, the entanglement is in the chain between the two, and by the one dimensionality of that requires you to have some kind of T junction. If you want to braid the two things, you have to do this, right? It's like a train set, and it's slightly more complicated, but the entanglement is essentially somewhere located between the two things. So the entanglement tells you whether whether the fermion state made by two of these guys is occupied or empty. But as I say, I can rearrange it. I need two of these Majorana zero modes to make a state I can put an electron into. But I could take this pair over here and this pair. I can shuffle them around. So I'm really somehow breaking the electrons up into two, or the fermion number up, and rearranging it. So it's kind of cool but complicated to. I mean, I can't quite explain it without mathematics. Yeah. Well, I mean, the basic description is you have an assembly of qubits. You create a certain you create them in a known initial state, possibly an unentangled state, and somehow the information or the data that you want to process is loaded into the system by creating an initial fixed quantum state, and then the program does some kind of gates or braiding or whatever, applies a certain set of operators to the system, a sequence of things, and it causes them to become an entangled state, and eventually you have to make some kind of measurement. But there's something called like a quantum interference effects, where in some sense you want to have a thing where the correct answer kind of shows up because it kind of maximizes some interference. So the rough kind of dream idea is you're somehow probing all possible solutions to the problem at the same time, and the good one shows up by a kind of constructive interference effect in some way that you're able to measure, right? And but it's difficult to explain in a kind of non-technical way.
Let's thank Professor Haldane once more for the nice talk.